Now it's time for a review of projectile motion. And just as a reminder, projectile motion is when something is moving in the x direction and the y direction. So an example would be a ball rolling across a table and launching off like this. Now as it flies through the air, it moves horizontally. So it has a horizontal displacement, while it also moves vertically, so it would have a vertical displacement. That's a key feature here with projectile motion, or two-dimensional motion in general. What is more specific to projectile motion is that the vertical motion represents free fall. And when we say free fall, we ignore air resistance, and we have a gravitational constant of plus or minus 9.8 or 10, depending on how accurate we want to be, meters per second squared. Typically, I don't call that g, I call that acceleration in the y direction. And taken as a vector, where direction matters, it's going to be a plus or a minus, and that depends on your coordinate system, so that'll be a key feature when we talk about solving these problems. Now another common projectile problem is, let's say that ball is still going off a cliff, but that cliff is angled. So the ball starts off in that direction. Not perfect, but that'll do. Still there's a delta x. Still there's a delta y. But it is a little more complicated, and we'll see why that is here in a moment, but or we'll show how to solve for that. But here I have my initial velocity. There's a vi in the y direction, and there's also a vi in the x direction. When combined, they give the initial velocity, like how fast the thing was moving, like actually moving when it left. This one up here, we have your vi, but you can't really see any viy in this case. It's all vix, so the vi is the same as the vx. viy equals 0. That is a significant feature of that type of projectile problem. That would be called a horizontal launch, where you throw something horizontally or launch something horizontally or run straight off a cliff. Of course, that's not advised, but that's that type of problem. Those problems, much easier. These require a little bit more thought. So we'll take some time to go over those. Oops, wrong button. It'll take us a little bit of time, but we'll see how that goes. Again, clearly I'm struggling with the technology. Eraser working? Yay! All right. So now let's look at an actual projectile problem and how we would use our problem-solving strategies for this. So main problem-solving strategies are the tables. We have a displacement in the vertical direction, how fast you're moving vertically in the beginning of an interval, how fast you're moving at the end of the interval in a vertical direction, your rate of acceleration, and the duration of the time interval. Now that is just for the y direction. And with projectile motion, we will often keep these things separate, the x motion and the y motion. The x table is simpler. It's a table of 3. And if you've been watching the other screencasts, you should recognize that a table of 5 is useful when acceleration is non-zero, and a table of 3 is useful when an acceleration is 0. So what I'm telling you is there is zero acceleration horizontally for a projectile. The only reason it accelerates or speeds up, slows down, changes its velocity is because of this gravitational acceleration that it acts just up and down. Just down. It acts downwards. So let's take a look at a problem. A horizontal projection. I have an object launched outwards with some initial velocity. Let's say it's 25 meters per second. And it's going to, it's on a cliff of height 50 meters. Common thing is find out where it lands. So coming up here to my table, these are all vector quantities, and vector quantities require a coordinate system. So it's important that you define a coordinate system. I'm going to say to the right is the positive x direction, and down is the positive y direction. Once I've made that choice, this allows me to say my vertical acceleration is positive 9.8, because this here points down. Down is positive, so positive 9.8. Since this is a horizontal launch, VIY is 0. That's not typically said in a problem. It won't say VIY is 0. Instead, it will say it is a horizontal launch or launched horizontally. The other piece we know is this thing falls down 50 meters. And it could be a positive or a negative 50 meters depending on my coordinate system. I'm saying down is positive. This thing went down 50, so I'm good. I was given an initial velocity in the x direction, and I'm asked to solve for a horizontal displacement. Now I'm going to walk you through how I think about these problems. It's super useful, I think, and it should help you. So what I want to find is something over here in the x direction, and I only know one thing. So in order to find my unknown, I need to know the other two. So I need to know the time in the horizontal direction. Now luckily, with projectiles, the time in the x direction is the same in the time in the y direction. So if I can find this in the y direction, I also know it in the x direction, and I can solve for what I want. So now I'm going to focus on my y table. Now I know 3 out of 5 things, and that's like the magic thing, the magic number. If I know 3 or more, then I can solve for whatever else I want. Right now I don't care about final velocity. I care about time. So the math model I would choose is the math model that doesn't care about final velocity. And if you recall from previous screencasts, that's delta y equals 1/2 at squared plus vi t. Now the vi in the y direction is 0, so this entire chunk goes away, and I have delta y equals 1/2 a t squared. I want that for time, so I want to get time by itself. First thing is I want to get rid of this 1/2 a, so I'm going to multiply by 2. I'm going to divide by a. That leaves me with t squared, but what I want is t, so I'm going to square root that. Now technically a square root has a positive and a negative root, but what I'm anticipating, well, what I would expect always, is for a positive time value, so I'm just going to use the positive root. Now 2 is just a number, y is a number we have, it's up there, and a is a number we have, so I could throw that in the calculator and get time. I'll leave that for you if you want to. Now that I know time, I know it up here also, and I could use a different equation. I could use, well, the same equation actually, but in the horizontal direction. Now in the horizontal direction, acceleration is 0, so I have delta x equals vx delta t. I have vx, I now have delta t, I could multiply those together, and I get my answer. So hooray, I've got that done. That's a pretty standard horizontal launch problem. There could be complications. I could ask for things that are a little more difficult. For example, if I asked, what is the final speed with which the object hits the ground? So I'm asking for VF. It's not a perfect drawing, but hopefully it'll do. That's how fast the object is actually traveling at impact. And I did not specify VFX, how fast it's moving horizontally, which would just be this up here because it's constant. And I did not specify how fast it's moving vertically, which would be this right up here. I just said how fast is it moving at impact. So that problem's a little more difficult. It requires some trigonometry. This is what I'm asking for, VF, which is going to be the vector sum of Vx and Vfy. Now again, Vx, we know it. Vy, we could find it and then dump it in over here. Now that means I've got two sides of a right triangle because x and y stuff always meets at a right angle. And to find this one over here, I would need Pythagorean theorem. So if you recall, Pythagorean theorem says a squared plus b squared equals c squared, or in this case, vx squared plus vy squared equals vf squared. So VF is going to equal the square root of Vx squared plus Vy squared. Now again, technically there's a positive and a negative root, but when I'm using Pythagorean theorem in this context, notice I'm not even putting arrows on top of these velocities. I'm not talking about them as vectors or where the positive or negative matters. This is just going to give me the magnitude, the amount of Vf. Okay, that's a little more complicated than the typical problem, but I could ask that problem. I believe it's been asked of you probably on homework assignments. So there it is, how to solve for that final speed or final speed at impact. If I really wanted the velocity, the other piece I would have to find is this angle. And to find an angle given sides of a triangle, you would have to use trig again. You could use sine, or you could use cosine, or you could use tangent. In this case, I might use tangent. Tangent of my angle would be the opposite side over the adjacent side, or the angle would be inverse tan of that ratio. And that would give me the angle measure, in case that was curious or interesting to you. Okay, so that's a basic projectile problem, a horizontal launch. Then in the next projectile thing, we'll talk about a non-horizontal launch. It requires a little more thought, a little more time, a little more trig, but it's still doable.